Okay, we're all here.
Yeah.
Okay. Okay, if everybody's here, we'll go ahead and start. Welcome. As you can see, I'm Bill Hanson, the Director of Competition Rules. We've got Ed Wilkie and Joe Pfeiffer, who are the other members of your judge team. And just glad to see you. And I just wanted to say to start out that I was largely quite impressed with your technical report going in there, and but I do have a few questions, and so we'll just kind of go round robin. My first question, the thing that jumped out at me, is that you were planning to use double pole single throw switches to arm your electronics. Are those like the ordinary just slide or toggle switches? Or what?
Yeah, they are toggle switches. So like toggle switch, you just put it on and off.
Right. Okay.
Mounted on the
what's
rocket
the yeah, right. So what's the G rating for those switches? How?
So yeah, it's not quite calculated theoretically, but since the switches are tiny, it should create little to no air resistance with the rocket's flight. So it should handle the G rating in any condition. That's our hypothesis on it. But still, we should let Sangram handle this as well, since he's the aerostructures expert in the team. So Sangram, please go ahead.
Hello, sir. So basically, to be very frank, we haven't calculated that much, but that's it. Next time we'll keep this in our mind.
Yeah, I mean, there's a traditional issue with these kind of switches that they're very sensitive to being moved around, either from the G load or the vibration, especially if you have them so that the way you switch them is along the long axis of the rocket. You know, you can
Yes.
Those things can turn off quite easily, and for that reason they're not commonly used. They're and most people don't use them at all. So I would when you do this for real, I would highly consider going with a different type of switch here. Okay, Ed, you got a question here?
Yes. Fin dimensions were discussed, and the statement was fin dimensions were set up by rule of thumb or thumb rule. What is that?
So basically, we just had some preferences, and according to it, we found out that the rule of thumbs for fin dimensions are most probably 1 times or 2 times the diameter. For example, the root chord was supposed to be 2 times the diameter of a rocket. So considering those, we considered a root chord, for example, is 30 mm. So we considered in a diameter of a rocket, which is 150 mm, and considering we took a 300 mm of a root chord. Similarly, for tip chord, it was like 1 times the diameter, 1.5. So we considered it 15 as it was 1 times. And if span is as far as concerned, we did consider it 1 times the diameter, but we were not coming into the margin, stability margin. So we increased it to 16 centimeters.
Okay.
Okay. Joe, do you have a question? And you need to unmute yourself.
Yeah.
There you go.
Well, I was muted because I wasn't talking. I liked about your project a lot is that you actually made use of your altitude. There's an astonishing number of projects that go to 30,000 feet and then deploy a payload at 1,500. I am curious, though. I saw graphs of predictions of expected number of muons versus altitude. I didn't see much quantitative there. Do you expect to get sort of a reasonable difference to really see something? And there'll be a follow-up on that.
So the muon count rate, exactly, right? You're asking about that, I guess?
Yes.
The Reznor-Forger curve and the Palmer models?
I'm sorry?
The Reznor-Forger curve and the Palmer model that has been discussed in the payload section?
Mm-hmm.
Okay, so basically what we understood from the various sources that we went over in order to decide for the payload, the Reisner-Forger curve is obviously calculated for extremely high altitudes, right? It is actually calculated for altitudes where the atmosphere doesn't even exist. And the altitude that we are targeting is about 10,000. So we do expect some sort of falloff to occur, but we are able to actually somehow make it in somehow get a plot that is a linear interpolation between the
Okay.
data that we can get from the payload and the approximations that we can make. And if we get a curve that somehow even has a least resemblance to at least one of these curves, we can consider that the payload experiment was quite successful.
Okay. You're only going at 10,000 feet. Would
Yeah.
30,000 have been a better choice?
It would have been a extremely great choice. Personally I feel so, because it would be in the stratospheric region at that point. It would be even above that, and we would be able to get even better results as we go higher up into the atmosphere. The 10,000, it's not really a great altitude for such kind of experiment. That is what we are just trying for this experiment in order to see if it's even feasible to have such
Okay.
kind of a payload in such a rocket or not.
Have you done a baseline at ground level just to see if your units will measure anything at ground level?
We were
s-
actually
yeah.
about. So you are taking as asset.
No, okay, you take that.
Okay. So basically, the entire muon detection experiment is based off on the Cosmic Watch desktop muon detector program, right? And we weren't able to actually manufacture the entire muon payload, and therefore we haven't been able to do any kind of ground tests with that payload itself. But what we have are data sources that have been collected from various different people who have done the similar experiments in the past, and we have a reason to believe that this payload might as well work if we use this in a rocket in the rocket application that we are trying to target for.
Okay, so are you planning on doing a ground test with it to
Yes
at
sir,
least?
yes sir,
Yeah, yes.
yes sir, we are planning
We
on
have
doing the
actually
ground
planned
test.
for it.
Okay.
Yeah, I
I got a
understand it's
question
in
on
Bell
your.
India right now.
Yeah.
Go ahead.
Yeah, yeah. It's only going to be 108 out here in the desert tomorrow, so it'd be pretty hot all around. I was very interested in your bulkhead system for joining your sections, and I saw that you did a lot of compression testing to make sure that they would handle the compression. But did you test for any other failure modes besides just straight linear compression?
So actually we did analysis more of a, and accordingly we decided on the same bulkhead system. To be very honest, it was based on the earlier versions of our bulkheads, But later on we did some in 2020 for 2020 event, we used the same bulkheads and did testing for ejections, so that's ejection charging. So those tests were conducted.
Okay, because the thing that the reason that the normal coupler goes, at least one caliper either side is
You're not audible.
Yeah.
Bill, yeah, we just lost your audio there.
Okay, I just changed microphones here, it looks like, but it doesn't, one of the things that we worry about is bending or torque loads due to the angle of attack of the rocket as it comes off the rail, particularly, out here where we can expect to be to have a significant wind. Have you looked at that mode of failure?
So basically, sir, we would want to actually launch it to get actual results such as this, but we weren't able to launch it due to our certain government reasons. It's not allowed. If you ask us theoretically, we haven't done such as theoretical tests. But we
Okay.
did use the same system for a couple of years, and it was more than expected what we got results, because from that we saw that it was not getting buckled, or it was not bending, so we thought it was the best.
Okay.
So we did some sort of like we did analyze the failures that happened in the previous flight event in 2019 event, and we actually redesigned the bulkheads according to that. So one of those was the compression chest thing, and so Sangram here redesigned that so that we could get better results out of it.
Okay. Okay. Ed, Joe, you have questions, other questions?
Yeah. When you guys were running your ejection charges, you said that you got a pressure of 24.67 psi. How did you measure that?
So basically, what we did was we calculated that pressure to be that pressure would be after the combustion of ejection charges in a closed vessel. So that pressure would be required to shear the nylon pins by which the body tube is coupled with the bulkhead. So we also calculated the shear strength of the nylon pins. For that, the pressure required to shear those pins would be required. So we use that pressure in the ideal gas equation, and by that we determine the weight of the black powder.
Okay, so what I'm understanding is you're basing it on the force it took to break the shear pins. Is that correct?
Yes. Yes.
Okay.
Okay. Joe, you get?
To follow up on that just a little bit, how much margin did you have in that? So how much force did you anticipate would be required, and how much force were you getting from the pressure?
So actually, we took the reference area of the bulkhead. So we used the circular area of that bulkhead, and it was something around 400 or 430 newtons as per the report. So we used that force, which would push the bulkhead, and which would shear the nylon pins.
So that sounds like you're saying no margin, that you calculated exactly what it took to break the shear pins.
Yes. So we actually use the pressure.
Okay, just
So according to actually, I would like to follow up on that. We did get the actual weight of the black powder from it, and we actually rounded it off to a higher number so that we can get successful
Yeah.
ejection between two body tubes.
Okay.
Yeah.
Okay.
Yeah. Typically, you'll try to get like double the force that you estimate you need to break the shear pins, and then of course you find out what you really need when you ground test it.
Okay. We're time short, so let me ask just one more question. In your video, you said that your initial sims were exceeded 10,000 feet by a pretty good margin. And then you said, well, the rocket's going to get heavier, so we're going to keep our fingers crossed that we're going to get close to 10,000 feet. So have you figured out how much heavier the rocket has to be to hit 10,000 feet based on simulation, or how much more drag you would need to hit 10,000 feet?
Yeah. Can I take it, Simran? Okay, so the weights that were put inside open rocket, like all the different mechanical components, like the nose tip and the bulkheads and the different avionics and payload, the mass was estimated actually through CAD, like putting the material in the CAD itself. So we got the weight from it, and that we did refer to different reports from different teams and found out different resources. And so they actually helped us find out that actual aerospace projects do get heavier once you try to manufacture it. And it's our team's prior experience as well that, well, once we manufactured, like we did get some error while putting it on a vertical machine center. So we are expecting to get a little bit heavier. So it's around 5%, but still, it's there.
Okay. Okay. Time is
time.
almost up. Yeah, one more question very quickly.
Yeah, real quick. On your parachute recovery linkage, I picked up that the quick link, hold on, the quick link that you're using may be too weak, not strong enough. Your parachute cord, your shock cord, and so forth, I think was rated to 2,200 pounds, but the quick disconnect link was at 800. So
So
that might be
basically, what we did, we actually used the cost recovery system. So basically, what we were referring the Fruity Shoots website for that. So as per the parachute which we have selected for the main shoot, that is the around 84 inches. So with that parachute, they have recommended that particular quick link, which has a working load around 875 pounds. And the shock cord has a breaking load of around 4,800 pounds.
right, but there was, like I said, the quick disconnect link seemed a little light as far as tensile strength for what you may need. You might go back and look at that.
Yeah, sure. We will
Okay.
look at that again.
Okay. All right. Well, thank you very much. We appreciate your answers. And then it's time for our next team. So if you depart, we're ready for the next team.
Yes.